ramble off stream with the people that do show up and start late, then like start on time every time. Because the people that show up and want to talk about secret stuff off stream, we can certainly do so. It just can't be recorded on the public internet.
Public internet is a scary place.
Public internet is a scary place. Let's make sure I'm not doxing myself. I don't think I am. I was here early the other week too. Yeah. Yeah, I just prefer the appearance of random chaos. All right, so with that said, this is a Pwn.College stream. We are here at CSE598. This is office hours. For those that are not familiar with Pwn.College, Pwn.College is a website that is free and open to everyone. As the website says here, you can learn how to hack. All you have to do is create an account. It is free and open. We ask for an email and a password. The only reason we want your email is so we can reset your password. We're not going to spam you or do anything nefarious with your email. How does it all work? Well, you just go to this website here, Pwn.College. Once you create an account and log in, you can click up here in dojos. You'll see that the entire site is set up as like a series of martial arts dojos, starting from an introduction to white belt, orange belt, yellow, all the way up to blue. Which is currently our kind of higher end material. To work with the material, you can click one of the topics here or scroll down and follow one of these classes. So this material is put out by Arizona State University and is used in a university course. If you are not in the university course, it makes much more sense to just follow along with these belt tiers. But you can certainly follow along with the class if you happen to line up with us. This stream is following CSE598, which kind of coincides with the blue belt material. And you'll see there's a number of topics we are exploring. We're near the end of the semester. Right now we are wrapping up our discussion on kernel exploitation. So if I click right here, what we'll see is there are a series of videos and slides that kind of discuss the topics at a high level. You'll also find a number of live streams, such as this, either embedded on the website or on our YouTube, which is just youtube.com/Pwn.College. So you can kind of check out that as well, which is a little bit more freeform, where we just kind of answer questions and poke at some scenarios, discuss concepts on the fly. Now, what makes this site interesting is that there are actually challenges that you can work with. Today, I'm actually going to be taking a look at level 6 here. So I can click either start or practice. Practice gives me a little bit more power, so I can do some debugging that I wouldn't otherwise be able to do. Start runs it in like a testing mode. And we see here it says, hey, we've started a challenge. What does that mean? Well, I can click either workspace or desktop up here at the top. We look at workspace. We get a VS Code-like interface. This is right here live in our browser. And if we, it's going to be tiny text, but if we ls/challenge, we see there's a couple of files here. These are kind of the binaries or files that we're going to be challenged to hack or exploit. The ultimate goal is to cat a file that's located at /flag, which, as you see right here, I cannot do. So we have to take advantage of the files located in challenge to somehow elevate our permissions and access this flag. So VS Code is a fine way to interact with coding. If you want to use some type of a GUI tool, for instance, IDA or Binary Ninja, you may need a more desktop-like interface, which we have right there from that desktop link up at the top. This gives you a fully interactive Linux desktop where you can utilize GUI tools to analyze these binaries. And we'll see here that I am in that same kind of environment, so I have access to the same challenge binaries. Now, if you are more like me, you like the terminal. And so we also support SSH, which you can engage with. Once configured, which is on the welcome page, describes how to set up your SSH key. You can SSH hacker at dojo.pwn.college. This is a me thing. Boom. And now we have an SSH connection into that same environment where we can work with this directly. With that said, we are here with some students that have some questions about kernel exploitation. Based on where people are at, as well as it looks like Twitch, people have questions about level 6. Okay. Let's poke around at level 6. I'm going to move whatever my do.c. How many olds am I on? Do.c becomes do.c newest old. Done. Okay. Now, so I'm in a tmux session here. My left hand, let's put the VM. Yeah, whatever. VM start. We'll vim do.c. Maybe. Okay. So hopefully this is similar to what we've seen already, and so it'll just be a bunch of boilerplate. I really should just save the boilerplate. But, you know, what if somebody only watches this stream? Then you got to figure out what is going on. Somebody says, right now I can get a use after free pointer to control the message struct. Okay, they overwrite the size, but also clobber the endlist head pointer and another pointer, and the kernel panics. So this sounds like a sane approach at a high level. If you'll recall, what was it? Was it level 4? Level 4 to level 5? We used modprobe path, to gain execution. And we ran into a problem where we were clobbering some pointers and things were getting, a bit nasty, and we were causing the kernel to panic. I think that was where I left our last office hours at. I said, hey, we overwrite this modprobe path. We looked at the VM logs and said, hey, null pointer dereference. And I was just like, yeah, you did that. It's your fault. Figure it out. Fix it. Right? And fortunately, for the most part, you guys did. Could this be a similar scenario? Garbage values worked for me. Says Twitch. Garbage in, garbage out. Right? It's like 90% of my code. That's why it's all named do.c. Right? We know what's happening. Okay, so let's take a quick look at what we got going on here. Level 6, I believe, is the first one. What is the hint there? Okay, we are working on the real Linux kernel now. So in class, I mentioned that we have the general purpose cache. So this is going to be interacting with that now. And so in module init, I don't see anything exciting happening. We're creating that kernel device here, create the proc entry. On Heap open, this is where that kmalloc trace is, which I showed last in class. Kmalloc trace is really kmalloc in disguise. This is a Binja phenomenon here. And so we are calling kmalloc with a size of 1b0. You'll note that we are mem setting that to 0, which was our problem in levels 4 and 5. That's all that's going on when we open. So we can trigger a kmalloc on open. We should also have ioctl. In ioctl here, we've got our same codes. 5703 is free. 5704 is stir copy. Okay, and this is stir copying into kmalloc caches from this location. Okay, I missed. Let's see if I can make that look cleaner. I think I know what's going on. Okay, the garbage in, garbage out conversation continues. Someone says they put in dead beef and it broke. Dead beef is certainly garbage. Okay, I'm looking for the Heap octal. We got the copy from user. Does this look a little bit? Yeah, that looks cleaner. IDA, way to go, IDA. So IDA shows us that the, where am I? Heap octal. And then I want this to be hex, hex, and hex. 5704 will call kmalloc. Make sure this is still, yes, 1D0, and it'll copy the flag in there. So our operations that we can do are malloc a Heap object by calling open. We can copy from user, so we can write into it. We can free that object, and we can make flags. Yes, so this is the 5704 is calling kmalloc with a size of 1D, hex 1D0. And then it is storing that in v6, right? And so we are creating a kernel allocation, storing the pointer in v6. We are then calling stir copy, and we are stir copying flag into v6. And if we're reaching the end of my my knowledge here and using these fancy tools, I think it's going to be my goal for the fall is to become proficient in one or two of these decompilers, like learn all the shortcuts. And what we saw here, so if you didn't see, I was in Heap init, or not Heap init, Heap ioctal, and we went down to where that flag value was. Where was the flag? Right here. We mash X for cross-reference. This is going to show us everywhere that location is referenced, either by symbol or as a memory address here. And we see that it is used right here, which is where I am already. And then it's also referenced to Heap init plus 15 and Heap init plus 21. So if we take a look there, what we see is this fill p open is functionally equivalent to calling it open in userland, right? It's the kernel's way of opening a file. And so the kernel is opening flag. The kernel is zeroing out this memory location that is just referred to as flag. It then will read from v0, which is, I don't believe that's actually a file descriptor. That is a rabbit hole. Functionally, it's reading from the flag file, right, into the flag variable, and it's doing that on Heap init. So when the module starts up, it has already read the flag somewhere into memory. And so the functionality that we trigger on, what was it, 5704, is the act of mallocing and putting the flag there. Twitch says, yeah, dead beef. Should have used beeflet. Beeflet's way better than dead beef. Isn't reading needed for a leak or something? It's always or something, man. Like, come on. And then we do not innately have the ability to read. So I don't believe I said we have the ability to read. But now we have some loose idea of what, I don't want to say primitives, what operations we can perform, right? This gives us kind of a starting place to reason about the problem space that we're in. And a good strategy in general is to have an idea, if you're not sure how to tackle the problem, understand everything that you can do and then model that interaction in code as a starting space. right? Because odds are you're going to need to perform those actions at some point in your exploit. So let's include one day. Anyone know all of the ones for open? All of the headers. I should start like stating them aloud as a mantra on every stream.
These are the sacred incantations.
The sacred incantation. Pound include systypes. Pound include systat. Pound include.
Probably need sysioctal as well.
We probably will need. See, you know that. I would have just guessed ioctal. But at the same time, it's probably a good thing that I don't have all of these memorized, because everyone gets to watch me open up man pages. So it's a
Your ioctal.
my ioctal. Don't you be telling my ioctal what it means. Okay. Let's make a couple quick notes here. I'm not going to write functions this time. All right, that was a horrible mistake. As far as I saw it, we had 5703, which is free. We had 5704,
which is flag.
malloc and put flag, and then we have 5701. Copy from user, so write to object, right? And the last thing, of course, that we can do is opening the module. We'll call kmalloc as well. And then just a personal note here, everything operates on OX 1D0, which is going to be an OX 200 kmalloc cache. Okay. One other thing that we should probably identify, which is not going to be there. Yeah. Let's do it. Okay. I wish I had like a stable Vim. The Vim that you see me demo is not the Vim that I use. What is this, like 8 space tabs?
That's huge.
Okay. So first thing we're going to do is we're going to malloc a kheap object, which we said we can do by calling open. So nfd is going to be open proc kheap, and we want it for read write. One of the things that we don't know at this point, like I happen to know, but that's not quite fair for you, is we know that everything is operating on a size of hex 1D0. And we know from the earlier challenges that this is on the hex 200 kmalloc cache size, right?
Yeah.
But what we don't know is which kmalloc cache is it interacting with. Do we?
I think at one point we looked and it was like kmalloc CG 512 or something.
Okay, how did we look?
It's proc slab info.
Proc slab info, okay. Let's do some things. Let's connect to our friendly VM here. We gave it like a 5-minute, 10-minute head start. So we are in practice mode, so we can sudo cat proc slab info, and then okay. There's a whole lot of stuff going on. My strategy here is I'm going to loop through. I'm going to open 20 times, but I also need to make sure I'm maintaining these objects. I'm holding on to them. So if I were to just run this and look at before and after, right now I would probably see no change because my program's going to end. It's going to close or release which will in fact call free on our objects. So we want to somehow block here. Is there a magic header for get char? It's just standard IO. Okay. So we will, you could tell me about my octal, but you can't tell me about my funcontrol. There we go. Okay. So we run that. Now it is blocked. I'm going to hit Control Z, so we've stopped, right? Since I didn't tmux and tmux. We mash it again. What do we see? What am I looking for? CG. We see these numbers.
That's not CG1.
That is not. Where's the?
There it is.
We see these numbers.
We want to look
And then we want to. So this is the after, right? What are you asking me?
Oh, are we looking at 512 or 286?
What are we looking at?
I guess we look at both and see which one changed.
Well, we got to do some math here. All right, it's high level math. I understand. We're only in a graduate class. Okay, 512 is a good number. So that's not the CG. What do we got here? Okay.
That's after 48.
That's the after at 48. And then right here, we're at 32. So that didn't quite map how we wanted, but remember that this is a general purpose cache, and so there could be other actions going on.
Something might have gotten freed.
Yeah, something might have gotten freed,
But like 16 is close.
Well, we could malloc a whole lot more and see if just more makes more. It's no fun if I get everything right. Okay, guys?
Oh, I'm sure there'll be plenty of opportunity.
All right. And then we run that again. So now we're done. And it didn't go back down. Oh, somebody actually listens to things that I say. This was literally the only demo that I had earlier this week. Yes. So just catting slab info isn't necessarily going to be accurate. It'll show like an upper bound where when I wanted to show what was actually happening there accurately, I was using the GDB plugin libslub, which we could do on here, but this also has KASLR, which brings us down another rabbit hole that I'd rather just avoid.
Okay.
Thank you. Thank you for listening. All right. Yeah, it's things like that that make me feel like my time is not wasted. Okay. So, what is our plan of attack here?
So we want to like spray a bunch of flags, or at least one flag, into that cache, and then get something that is able to read it.
Spray. What are we spraying? Flags?
Flags.
Spray flags. Okay. Then
Allocate something that is able to read said flag.
allocate a thing and read flag. Okay. So what does spray flags look like?
We open a bunch of proc K heaps and call 5704 on it.
Well, let's think about that. So the statement was we're going to open a bunch of proc K heaps.
We don't need to open a bunch of proc K heaps.
We don't need to open a bunch of proc K heaps.
One, we just need to call 5704 a bunch of times.
We need to just call 5704 a bunch of times. What's the difference between doing those two actions? Opening K heap and then calling ioctl or 5704. Opening K heap, calling 5704. Like, what's the difference there? Does it matter if I open a bunch of K heaps? And if so, why?
Because when you open a bunch of K heaps, they will allocate empty stuff before that?
Empty stuff.
Or they'll malloc something when they're open.
Yes.
Might not contain the flag.
It will malloc something that certainly will not contain the flag.
Yeah.
So that was the one thing that we saw, one of the things we saw on Heap open.
Yes.
On open, it's going to kmalloc a hex 1d0 object, but we see that this thing is malloced and then mem set to 0. So we think about, I don't want to draw it, right? But if we were to think about it as our slot, I'm just going to draw it with invisible ink. If we were to open and then ioctl, then open, then ioctl, then open, then ioctl, for every flag, we are creating a Heap object as well, right? It's not necessarily a Heap object. Do we know that it's a Heap object? It is just some hex 200 object. Right?
One of our slots is filled with things.
Yes. And there's nothing wrong with doing that, right? But is that advantageous for increasing our odds?
It decreases our odds, I think, of hitting.
Well, it changes our entire strategy. Okay. So, like, we could do either one of these. In the first scenario, let's see. Oh no. Okay. Do you guys know? Yeah, I know. I'm gonna tangent the heck out of this. Okay. I've been trying all semester to remember to utilize technology, right? We have technology now. Oh no, but I didn't prepare. Okay, I don't know what'll show up if I hit the button, so I'm not going to do it. So I do have to use a marker because then it would look better on stream. Maybe next semester I'll get to it. Oh wait, I can hide my screen. We have that technology too. All right, we are abandoning the idea. Technology failed. All right. Sometimes, they'll stick in the sand is just better. All right. So I'm not going to make it too complicated. We're going to go with a nice tic-tac-toe board. So if this is our page layout, right, and we open, we would have, and then ioctl, we'd have a Heap, and then we'd have a flag. And then we'd have a Heap. This is assuming this is in order, right? And then we'd have a flag. Maybe there's a Heap here, then there's a flag there. Then there's a Heap here, then there's a flag here. Then there's a Heap here. Does this scenario that I drew here, is this more advantageous to us or less advantageous to us than if I just went F, 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 Heap?
Less advantageous because I think in the second scenario where we're surrounded by Fs, once we free the Heap, we know there's a flag next to us. Whereas in the second one we don't necessarily know there's a flag next to us.
Right. So I'm making a couple assumptions with my drawing here. One, I'm assuming there's no other objects allocated on the slab. Right. And so there is a default fail state just if there was some other object out there. We can get around that by allocating a lot of things to fill the prior slab and hopefully get into the next one, right? But if we consider the first scenario, our only failing case, if we're trying to make sure that we have a Heap object behind the flag or in front of a flag, right, is if we are in the last spot of the slab or the first spot of the slab, right, depending on what we're trying to do. If we go 1-to-1, how many fail cases are there? There's significantly more fail cases where our Heap isn't placed in a location that we are interested in And we have to manage all of these K-heap objects and keep track of them, which, isn't that hard. Right? There's only, 4 of them in this picture. But it complicates the scenario in a way that doesn't help us. Doesn't mean that this can't work, but I don't know that that is an advantageous scenario.
We should do ourselves some favors.
Yeah, like let's try and not make it harder than it needs to be. So I failed to activate technology, and Twitch points out if they were a monkey, they'd say more flags, less other stuff, better. Well, maybe you are. I don't know that you're not a monkey. Super intelligent monkey on Twitch. Okay, so spray valves. Let's spray some valves. And we do that with, we said ioctl on the file descriptor. Look up at our notes here, 5704. And then I need to have, do I need a fancy request object again?
I think it failed. We don't have one.
I didn't pay attention. Every day is a new day for me, okay? Yes, we are doing that same thing we saw in the earlier challenges where by default we are copying from user the argument from ioctl. So let's make that. Wait. Let's see if we can do it as an anonymous struct. What do we need? Standard int. We don't really need, but man, does it make it nice. And what are these two things? Putter and size. That'll work. Hack the Planet is raiding with a party of 19. Well, thank you, Hack the Planet. All right. Hopefully that is valid C. Then the other thing I need is some type of buff. We will make it a page for good measure. Okay, so now we have that. We have our global inside of main. We will set footer equal to buff. We'll set request size equal to 1D0 is a good number, right? We've been using that already. Hopefully that's not a major surprise. Now that there's other people watching, I got to get my tabs and spaces right. Okay, it gets a little embarrassing. All right, let's see if that compiles. Yeah, I'm okay with that. The only warning here is a type conversion, but as we know, warnings are suggestions. How many of these do we want to do?
Twitch said 39 at one point.
39. Was that just an arbitrary number, Twitch? I'm curious. Like, was 39 chosen with purpose? Or was this just the monkey threw a dart at the wall and 39 hit?
Is it still 16 objects per slab?
Question. Is it still 16 objects per slab? Well, I think I still have the VM hiding up over here. It is... Yeah, I'm going with 8. Does that make sense?
I mean, I guess if they're bigger and is it in a 8? No, it's not a single digit number.
We gotta look at the whole shebang now.
Yeah.
Okay, so let's look at the head of this, and then let's grep just what was it? Kmalic CG512.
Yep.
Okay. So active objects, number of objects 48, object size 512, objects per slab 8, pages per slab 1. We got a math. Is this math? You can't ask me. I already made my math here.
40,000
Oh, well, that is 4096. We did it. All right. Well, if you ask that question enough times, eventually hex starts making sense to you. Okay?
All right.
That's why it's important to just do it and verify, and then it just gets embedded in your brain. So yes, 8 objects. So 39 doesn't seem particularly relevant, but hey, whatever, we're there. So we allocated 39 flags on here. So now we have some kind of scenario that has lots of flags. All right. What are we thinking now?
So we are theoretically now on a slab with a bunch of flags. If we then open a new KH object,
The other thing that I'm sorry.
Yeah, go ahead.
I just think it's worth pointing out. The other thing that we know here is we allocated a kernel heap object 39 allocations ago.
Yeah.
So we have some K heap object hiding like slabs back. I don't know if you can see that one. This room is just covered in monitors. Right, so slabs ago we had a K heap object. Now we just have slabs full of flags, right? Because we chose 39.
So in order to get something that we can free, we're going to put a new KH object into the slab we're currently on.
So we picked 39. I don't know why we picked 39, but we did. But 39 is large enough to where it's definitely more than 8.
Yes.
Right? And so we've definitely blown past and made more slabs. Okay? We've definitely done that. What we don't know is what is the state of the current slab. Right? We could, I believe you were proposing, we allocate a K heap object.
Yes.
And then
free it. So
we free it.
So now we have like a pointer. Because this, I think this module still has to use something free. After we free it, free a KF object itself.
Question was, do we still get a use after free primitive here? And so if we go into our ioctl, we look at the 5703, it calls k free on the private data. It does not null it out. So that means in our 5701, we can use that pointer after it's free. So we do get the use after free, but what we are limited to is copy from user, the request size, and we know from earlier here, the request size must be at most 1D0. So you want to put something here and then free it.
And then so we can use that free to like put something in there later. And then
Okay.
slow into it. It's my thought.
I don't dislike it, and it can work. It absolutely can work. So if we were to make a K heap go right here, then we free it, and so this is now our use after free. That could work. What is our requirement? What are we trying to achieve here? What do we want our relationship to our use after free slot to be to a flag? Before.
Directly before one.
Okay. Now we just arbitrarily did 39.
Right.
Okay. Is there a better strategy than arbitrarily allocating 39 to increase our likelihood of creating this scenario? I'm going to argue that there is.
Cool.
Okay.
Is there a way we can know if we've gotten to a new slab?
Well, we said that there's 8 objects per slab.
Yeah.
All right. So if, in the worst case scenario, I allocate 8 objects, I'm on a new slab. Right?
So if we allocate 8 objects, like we know we're on a new slab. The new slab is questionably full of flags.
Right. The new slab. Let's clean this. I think it's way more fun with whiteboard. What am I think I mentioned this already. One of the best purchases I've made is a personal whiteboard. So we have some slab that is just this mystery, right? And if we allocate 8, if we call kmalloc 8 times, then we know we're on a fresh slab. And what did we know? What did we change here? What knowledge did we gain or guarantee did we gain by doing this?
These are either all empty or have flags.
Right. There could be other allocations going on for the record in the kernel that could be on there, but we have drastically increased the likelihood that these slots are either free or flags.
Right.
So then we have some number of flag. I don't know how to call free, but we have something like this, right? Some arbitrary number of flag or free. Now, what do I think I want to do?
We make a new KH object.
We make a new K-heap object. Okay, I like this.
And then we get 8 more flags. Is my thought, please.
Then we get 8 more flags. Okay. Here's our K-heap object. And then, well, we want that there. And then we go 8 more, which in theory means we have this state.
Yes.
Okay. Does this feel better than what we were doing before? Does it feel like this is a better likelihood of us getting
something can still mess us up in there?
But we like
much more reason, or
better odds. Yeah, we got better odds. Yeah. All right. Cool. So we're going to spray not 39, but 8, and we actually chose 8 for a reason. It wasn't just dart at the wall. Okay, then we want to make another K-heap object, which we're going to call this the, I don't know, front FD. Okay, so we are going to malloc a second K-heap object. Spray flags, so we know we are on a new slab. Okay, then we fill that slab with flags. Spray flags on the slab, on the fresh slab. 8 feels like a good number there as well, right? That's enough to fill it no matter what. So now you've created this scenario. Question, and there probably is an answer here, but I don't. Oh no, we don't have. Okay. All right. See, if I referred to my own notes, I would have the answer to my own question. What I was going to ask is, well, why don't I malloc and then free this and then fill it with flags and then just read what I want? Well, the answer is I can't read. I can't do math. I can't read. You know. Maybe Twitch isn't the monkey. It's really me.
We're all monkeys now.
Yeah. So now we have this scenario. What are we thinking here?
We talked about messages last class.
I'll try and bump you up a bit here, Twitch. So, yeah, we talked about this this message.
Right.
Yeah. What was cool about message? Let me find her.
You could manipulate the size of a message, so it could go into whatever cache you want it to go into.
So one of the cool things about message is, as a user, we can influence the size of the message that is allocated. And so that is pretty nifty, right? Because that allows us to target allocations in specific caches. And then we also happen to know that message deals with user-controlled data, so it will end up in the kmalloc CG set of caches, which makes sense, or it makes sense because that's its purpose, but it's beneficial because that is also what we're targeting here. Cool. So we did our shenanigans here. You said, I want to free this guy?
Yes.
All right. So we are going to free the kheap object that should be chilling on the fresh slab,
Should be front FD.
which is front FD. So that's going to be an ioctal on front FD. 5703. 5703 is correct, sir. Okay. So now's the tricky part. All right. Now we got that guy, and he is currently a use after free write.
Yes.
You said message. How do I make a message fit in this hole?
We make the message size, I think, what, hex 200 minus 30, because 30, or hex 30 is the size of the message header.
Okay. So the comment was, we got to go update our plan of attack. Alloc a thing and read the flag. Well, we got to elaborate on this now, right? We're doing more than allocating a thing. All right. We've improved this whole strategy. Okay. We fill current slab. We get a kheap on fresh slab. We fill fresh slab with flags. Oh, flag allocations. We are then going to free our kheap object from the fresh slab, which gives us a use after free write, like write only. And now we are going to harness the power of message to fill the freed slot. All right, and our comment on message was message is a header struct. So there is, it's actually better probably if I just look at the slide. There is this message struct that exists. Do I like that? No, I don't like that. That's not what I want. This is what I want. There is this struct message that is hex 30 bytes in size, and it is the header data of a message that is passed. And we create messages using message send, and we can free messages with message receive. Right? It works as a first in, first out queue. And so we create a queue, and then we can pass these messages into this queue. But the representation inside the kernel is these 30 bytes, which is the header of the message. And then, as the comments here indicate, the actual message follows immediately. And we get to control the size of the actual message. So we want to make a message of the size OX200. How do I do it? How about not you? You were there. You remembered something that I said. Do you remember how we made messages? Something about a queue. Okay, that's fair. I'll take it.
I remember you said you made like a separate queue for each message because it like blocks or something.
Okay, something about queues and blocking and okay, that's fair. That's fair. I kind of just flashed something on the screen and said, here's some magic code that's going to do it. Number go up, number go down. Right? I don't blame you there. But you know what else I did? Man pages.
Of course.
Yeah. Now Twitch says they have a good question here. Why are we interested in messages? So Twitch is asking, but what do we abuse in message? Is there a pointer we can overwrite? Is like why do I want this message thing? Well, this is where we go back to the amazing class stream that hopefully is a one-off and I never do again, where I spend most of my time showing slides. We were talking about what are desirable properties of kernel objects, right? Somewhere in here. Yeah, good old heap spraying. We were doing some heap spraying stuff here, right? This was a useful slide deck for what we're doing. Desirable objects. There we go, desirable properties. A controllable object size, which we are already playing around with as an idea with how do I get something that is exactly hex 200 to fill this specific hole in this specific cache. Okay? Message has that property. Circumventing copy to user or copy from user, right? Circumventing that hardened user copy protection. Well, this particular challenge doesn't have hardened user copy, so that's not really something I care about today. It is something you should care about in future challenges. Object pointers, function pointers. Okay. Does message have pointers that are interesting? Yes, it does. And in fact, if you were to click on the old recommended reading that's been chilling there for the entire module, way longer than the slides, there's some pretty substantial write-ups that demonstrate how various pointers can be used to create, for instance, your own use after free, given that you have something, right? Messages have the message header. Where am I? Explaining the kernel. Have this list head. This struct list head is a doubly linked list, so it's a next previous, and that is how they track the messages that are in a queue. If I am getting this correctly, definitely double check anything I'm saying here. And then you also have this message segment pointer, right? All three of those are interesting. I don't know what security is, but it appears to be a pointer, right? Basically, if it's a pointer, it's something that is interested, it's something we could be interested in corrupting, right? And just like talking broadly here about kernel objects and why we would care about them. Because it's not like message is, my gosh, you must use message. There's lots of kernel objects that contain a pointer. And so if you get a use after free and there happen to be pointers there, it's worth investigating how those pointers are used. Now, for this particular challenge, I don't believe we have to mess about with pointers. Because as this slide indicates, there is also MTS, which determines the size of the message text. Because remember, the size of the user-defined part of the message is variable. It could be 8 bytes, it could be 100 bytes, it could be, hex, a big number of bytes, some large number. I'm sure there's a cap. And so the message header tells us how many bytes of user data are there. And in fact, that's kind of what we are influencing when we create this message that fits in this hole, right? So we said that there was something about queues and message get, message send. I don't know, man. Robert showed some code and then I took a nap. I don't blame you. All right, I took a nap before this. Man 7, message, that's not the man page I want. Where's the good man page? MQ Overview. So you have to go 7 for that one, if I remember right.
I think we just do normally, it just regress it to 7.
It could.
Oh, it could. Oh.
It could. Yeah, you're probably right. But like I always think it's cool when you get the 7 because like the 7 is like this overarching like subsystem, right? 7's not a man page you typically run into, and so it's cool that it's 7. Right? So this describes how message queues and messages work in general. Wait. Somebody's having a thought here. So wait. We can just make it leak to us the entire slab, basically. And then somebody else says, yeah, pretty much, man. Like, what if message small? Then we make message thing big. and then we receive the message, right? It would be big message, which would right, which would include the flag. Like that's really what we got going on here. Like in theory, that should work. That is our game plan at a high level, and that is, I believe, what somebody was saying. Oh, I'm looking at the wrong thing. Somebody earlier was saying like they were attempting this, but they were getting some pointers blowing up and like something crazy there. And so, depending on how we do on time, we might get to encounter the exploding pointers ourselves. Then it's going to be like, yeah, I don't know, man, that's your problem, right? But we hopefully, like I kind of made fun of it, but it isn't that complicated, right? What we're trying to do, if we keep things simple, we draw some diagrams, and you just say, hey, how does this work? Right? And you can make it sound real fancy. You can be like, oh, we're on the nth slab with the 5th slot, and then we freed this, which is going to dynamically cause something to change, and then we overflow. Like, nah, man. You put a small message here that's the right size. We make it think it's a bigger size. Hopefully, when we receive it, we'll read more than what's actually there. So back to our man page. There were the system of queues, and we can create a queue with message get. This is where my code is going to drastically degrade. So we have some message queue ID, which is going to equal message get. And if we look at the man page here for message get takes, it needs IPC and sys message. Let's bring those in. Sys IPC. What was the other one?
Message.
Was it just message.h?
I think it was sys.
Oh, I'm trying to move through vim buffers instead of sys. Yeah, it is sys message. Cool. The interesting thing here is, as we've been writing this code, how much time have we spent in GDB?
Not so far. Wait, no, we looked at, no, we didn't.
We haven't touched GDB at all, right? Because if we have a solid conceptual understanding, we should be able to build out most of this, and then once something doesn't work, that's when we can go to GDB, right? I don't need to just immediately drop into GDB, because the conceptual understanding, in my opinion, is much more important than being able to delve through all of the kernel structs in GDB and kind of navigate that mess, especially since the tooling isn't necessarily the most user-friendly. If we can avoid it, we certainly should. Now, it said it wanted a key, right? What is a key? We search for key. It is a key T, message key, something, key.
It says it's like a key T struct or something.
Yeah, it says key T. Tell me what a key T is, man. Flag field, key T. No love. Let's go back here. Does it give me a key? No. Was there a related man page? I don't want to go all the way to the internet.
We can't just man key T, can we?
No. That would be too nice. Like, I know the answer, but I want to find the answer. Like, all of these shared object things use something that's similar to a file path, but they aren't necessarily a file path. If you were to look at, let's see, key T, no. Just checking the related ones here. SysV IPC. Let's try that one. SysV IPC. Key. All right. Does it say what a key is? Like, it's not fair if I'm just like, I have this magic thing. Okay, there we go, maybe.
IPC private key is a key.
So I was talking about message IDs, which identify the queue. Dang, okay, it's bringing me down. We go down this rabbit hole. So you end up with a like magic token. Well, I'll have to just consult the
There's
goose.
a bad page for F.
Yeah, that actually is.
Oh, okay.
That is the answer, right? But I was hoping that it
Would say it somewhere.
existed somewhere else, right? In like some example code. So it converts a path name to a key or a token, right? We're going to tokenize some kind of path name. And this kind of fake file path exists in a number of IPC mechanisms. Like if you ever try to do shared memory, you can define a file name that is, and it ends up in, I think, /dev/shm. Don't quote me on that. I'd have to reread the man page. But you can create a file that is a pseudo file that represents some region of shared memory that other processes can access. And you define it by a file path, except it's not actually the literal file path. So if you said /Robert, it wouldn't be @/Robert. It would be @/dev/shm/Robert, right? And so it puts the root of that like pseudo file somewhere else because it doesn't actually exist on disk. And so we can F2K to get a token. Watch, it'll actually be like /shm instead of dev. You know, whatever. That's what man pages are for. So I need to make a key T, and that's going to equal what? F2K. Path name and then a project ID. I don't know. Leb6. What is my project ID? Well, we could just put 0 in all sorts of places, but we should probably have some idea of what it does, right? So the project ID functions as a like pseudo randomizer. So like my /leb6 and then your /leb6 are not the same leb6. That's the act of tokenizing, right? This leb6 is my internal identifier. And then this is my hopefully random number that I've generated that keeps it private to me because no one else is going to guess the secret number. Okay. And so these two things create the token that is the key. So we have our sweet key. We go back to message get. Next thing it wants is message flags. I'm a believer in null. After I just said let's read and figure it out. All right. No, there probably is something we should set. A new message queue is created if key has the value IPC private. If key has the value, but key was our magic number.
The message queue if key exists and IPC create is specified in message flag. So we probably want IPC create.
Okay.
It's like this queue theoretically doesn't exist yet.
Theoretically, this doesn't exist. We want it to exist. All right, we're happy with that?
Seems good.
All right, that feels like a thing. Okay, so we've made this queue. So there's something about queues. The way that we send messages is by sending them with message send, and message send, very surprisingly, requires this queue. That's why we had to create it. So we're going to send a message down the pipe with message send. Some message. Is that right? No, it wants the ID. Message queue ID. Then it wants a pointer to my message, and then the size. Okay. Now we noted message, which is the header, is OX30 bytes. So we take target size minus OX30 equals our message size to pass to message send. Somebody says, how can other processes read it since it's used in IPC? So remember, IPC is not necessarily public. Like maybe I just want to communicate with my child. So like in this case, what if I forked off a child? Then the child would still have access to the message queue ID and could interact with it. And so that would be, for instance, something private, if I want to do private communication with the child or not. If I wanted to be like some global queue where other things could interact with it, if we would read the man page, there's going to be some kind of flag that we can set that will make it accessible with this message get, right? What they would have to know is they'd have to be able to generate the same token. And if we read not ms get, but message get, if we were to go back to the man page for message get will create or obtain the queue based on the identifier. So some other public process, assuming it wasn't specified to create a private queue, could call message get with the same identifier, and they would obtain access to that same queue. You see a similar mechanism with like mmap or shared memory, where it's a matter of how the creator decides to expose it. Definitely worth like messing around with in like your own toy program to see how different IPC things work. Right. So right now we've at some point seen like pipes. We've now seen message queues. There's also shared memory, which you can do with like mmap. There's lots of reasons you may prefer one over the other based upon your use case. Cool. So we had this queue. We're going to message send. That was not this page. That was this page. I need a pointer to my message. How do I make this message? I got star message P. What are the rules of message P? Message P argument is a pointer to a caller defined, so I get to decide what this thing is. Structure following the general form of a long followed by unknown blob of data. How do we want to represent this?
We could just make that structure there, or we just like.
Oh, you're so proper. You're so proper and good. An employer will love you. No, I like it. I like it. All right. We're gonna make this struct right from the man page. It's so good. I would never do this. That's why I let you guys guide. Long M type, and then a char buff of, I don't know. I like a page. A page is just a good number. Okay. So then I need to have one of these things. Oh, wait, we'll make it an anonymous struct. We're getting fancy now. Boom. All right, so we got this other global. And so we want to give it the address of message buff. All right, our third argument was the size. Based on our notes here, our size should be hex200 minus hex30.
It's like hex 1B0 or something.
We could do math, or we could trust the computer to do the math. The computer is pretty good at doing the math. All right. I'm good at drawing pictures. All right. The computer is good at doing the math. So whatever that number is what I want the size to be. And the last argument was message flags. Do I care about this message flags? So this as IPC no wait, which does kind of what it implies, right? Do we want this to block or not? Okay. Because maybe you want to block on the queue because you're waiting for a message to then perform an action. Maybe you want this to not block and just immediately return. In this case, I don't care, right? Like I kind of care because I want the message to go there.
Right.
So if it doesn't go there, I'd rather it just hang than fail and look like it worked. Yeah. So I don't want IPC no wait. And nothing else here looks particularly interesting, so bam. Yeah. Now, if since we're writing good code, what is the return value of this thing? On failure, both functions return -1. So let's, if you're less than 0, we are going to p-error message send, bad stuff happened. There I go, hitting that tab button, man. Okay. So that way we'll have some, and we'll even exit. All right. Look at that. Look at that. It's like a real program. Okay. So after all of that, we managed to put a message, hopefully, right here. Right? There's a lot of poking around for that. What's the next thing I want to do? I want to try and mess around with that size thing. Okay.
Yes.
There's something else we missed here. So we made the message buff.
Oh, do we all put something in there?
I don't know, do we?
Oh, thank you.
So someone says yes, probably. Some people are shaking their head no. It's a good. I don't know, man. Does something go in there? Well, let's go back to the. We defined this struct. We went all proper here, right? Do these values have any meaning?
Oh, M-type must have a positive picture value.
M-type must be greater than 0. All right, so at a minimum, we probably want to do that.
Yes.
Okay. So, this was a requirement to send the message. M-type must be greater than 0. All right, what are we doing now? We said we want to overwrite the size thing of the message header and of the message. With our use after free pointer. How do I do that? We have the use after free pointer that came from opening. I can write, I'm going to go back up to my notes here. Copy from user, hex 5701 with the ioctl. We're going to ioctl on, what do we call this guy? Front FD. Front FD, OX 5701, and then we got to give it our request. We probably want to set request to be something. If you'll recall, the way that we get to perform this right is by setting the values of request. We currently have request size equals OX1D0, which I'm going to keep for the time being, just to be explicit. What do we want to set the other thing to be? We already know request pointer equals buff, so then we need to set buff to be
need to recreate, or not, maybe not need, but we probably should recreate a lot of the message header and just make a change in size.
Recreate message header. The change size.
Like, presumably, not all the message header needs to be strictly accurate. Like, there's a couple of pointers in there that you can probably just hover. And they'll run into the issue that the other person had.
Okay. Well, like we don't know what the other pointers are. Like this is where we're gonna clobber. I'm gonna be like, I don't know, guys, I'm bailing. Where is our pretty diagram of the message header? It's further into this. Okay. So what do we know? How deep into our buffer do we want?
We need to be into at least size T.
Right. So we're going for here.
Yeah.
Based on this struct, you can't like guarantee this universally in C. But can we reason where this is?
Size T is a 32-bit int, or is it 16-bit?
Size T is an unsigned int, but I don't have to actually concern myself too much with size T. I have to know about the size of the things before that. The list head, we said, is a doubly linked list, so it's 2 pointers. So that's going to be 8 bytes, 8 bytes, gets me 16. M type is a long. 8 bytes. All right, so now I'm 24 bytes in, and then that gets me to this size. Right? Hopefully, I'm not trying to like overwrite the thing.
I don't think we need to overwrite that.
Twitch does say the M list is hex 10, a long is 8, so MTS must be at hex 18, which is 24. Same math. I'm glad we came to the same conclusion. It's a good sign. Amazingly, we still could be wrong because you don't have that guarantee, but it should be the case. And they say M underscore TS is the 4th 64-bit value. That also aligns with our math and then Twitch chat's math. So, okay, so somebody must have exhaustively found this as well, and we all came to the same place. So let's generate some compiler warnings. All right, let's make a unt64t pointer, and we're going to call this. What was that thing called? MTS adder, and that is going to equal uint64t star of buff plus 3. I'm a believer there. That feels good. What do you think? We could have alternatively incremented buff by 18 as a
Hex 18, yeah.
Hex 18 as a char pointer. Should have gotten us to the same place. Here I'm casting it to a 8-byte pointer and then incrementing it by 3, which should still multiply to hex 18 to be the same place. All right. We then set MTS adder. I'm scared of pointer arithmetic, so am I. But I do it. I do it for you. What's a reasonable number? Hex 800 feels like a reasonable number, right?
Sure.
If these are 200, my base case is like hex 400, and so that should get me access to several slots past, right?
Is there an issue if we like try to pull from outside the slab? Or is that just going to be like random data?
Question, is there an issue if I try and pull outside of the slab? I don't believe there is an issue, but you don't have any guarantee about what that data is, right? You have no guarantee that any slab is contiguous with another slab, You only have the locality guarantees within a slab. And so you may be able to access something, right? It's probably readable memory, probably writable memory. But it doesn't serve any use for us.
Right, right. I'm just wondering, like, is it reasonable to just try and grab the next 8 objects?
I'm wary to do that because at some point, message is going to complain.
That's fair. Yeah.
Right? I don't know what the cap is.
800 seems reasonable.
But like 800, I got decent odds. I may run it a few times. Maybe we get something. Maybe we blow up. At the beginning, Twitch told me this is all going to seg fault and explode because of pointers, right? And I really don't have an answer for that at the moment. So let's see what happens.
Right now, we're overwriting mlist and whatever the other thing was to 0.
So right now, we don't have that guarantee because we didn't initialize. What's the word? We allocated the not that buff, this buff.
Yeah.
We allocated this buff, but we didn't initialize its value. So right now we're overwriting it with something, but we don't necessarily know what it is. It might make sense to set it to be something that we know. So when this explodes, we know what we did. So before that, let's mem set buff to be 0 for a page. And then if I remember, memset comes from string.h because it's weird enough that one I remember.
One last thing for our request size. Do we want to be writing the whole 1D0?
Okay, so that is a good question. Do we want to be writing the whole 1D0? Do we need to? Do we gain anything from doing that?
We clobber the pointers below the.
And is that helpful or hurtful?
That introduces more opportunities for error.
All right, right. We probably want to mess up the smallest number of things. So what do we want the size to be? What's our hex?
20.
Okay, someone believes in hex 20.
So we're like overwriting 4 8 byte variables essentially.
Yeah, like that makes sense to me. We are overwriting the first hex 18 bytes right here to get to the thing that we're interested in, which is the MTS, or the size of the message, which we're giving it 8 bytes. So yeah, all right. Cool. So that does the overwrite. What else do we need? How do I get it out? Message receive. So we must now read our message, our big message. It's very large. Our very large big message must be read. Okay. And we do that with message receive. It's always, okay? Like that's the beauty of like starting everyone in 466 on like day 1 with read the friendly man page, right? Like it never stops being the answer. Every once in a while it might be like ChatGPT, but like man pages are source. Man pages source GDB. That gets you like 95% of the time what you need. It's one of those 3 things. All right, so message receive, it wants a QID, it wants a pointer, it wants a size, it wants a lot of stuff. Okay, so we have a QID, we have a pointer. Can I just reuse that same region? What did we use when we sent? Message buff. Just reuse that same region of memory, right?
SQID has an underscore.
It does. Okay. What's our size? Same thing?
No, not Taylor, is it?
Okay. That was tricky. That was tricky. I did note that it was very large. 200 is just not large enough. And then we have message type and message flag. So what do we got here for message type?
Isn't that what we set before in the message book?
Look at the screen.
Oh, I see. Okay.
Aha.
Yeah, so it should match what we wrote before, right?
So
So we're going to the first message into a type message next, right?
if the message type is 0, you're making up words as you read.
Okay.
It doesn't say greater.
Oh, I see.
That's why 0 was an excluded number, right? So when we send, we can designate some encoding for what the message is that we're sending, right? But then the person on the receiving end can be like, well, just give me the first thing that was thrown in there, or give me the first message of type 1 or of type 2, right? And so you can filter through there on the receiving end. That's why it has that encoding, and why 0 is an illegal value to send. Because on the receiving side, 0 has a special meaning, which is just give me whatever the first thing was. I don't care about the encoding. So,
You can use a negative number. That's funny.
can you? If it's negative,
It's less than 0.
then it will be the lowest type, less than or equal to the absolute value. Yeah, maybe this is a generic protocol for IPC, and how you decide to wrap that for your use case, that is something that you may totally want to do. I think it's clever.
Oh, yeah, because you can might be like, I want everything of this priority or lower or whatever.
Yeah, maybe it's a priority. Maybe it's message types 1 through 20 are valid states, valid messages, and then higher than 20 are error messages. Or I'd probably do the reverse, 1 through 20 are errors, and then others aren't. If there's give me something that is an error, right? And maybe I do that non-blocking because we saw that we could do that on the receive side, right? So non-blocking, if there's an error, let me know. Otherwise, just don't wait for an error because we don't want an error. Just check for an error, and if there isn't, we'll keep going. Right? It's a very flexible protocol here. So, for our use case, for our special program that we're writing here, what do we want?
We just want the first thing. Right?
We just want the first thing. We only put one thing in there. So 0 feels like a good message type. And then there was message flag. What do we got there? That's just the old no wait thing. Let's make him null as well. Okay. We're writing a proper program here. We aren't using functions, but we are checking for errors.
What does it do to return?
It's a good question. Return value on failure. Both functions return -1.
Otherwise, return 0 and it's actually copied.
So we'll care if it's a negative number. If it is a negative number, message received. Bad stuff happened. We will exit with 2. Fancy. Okay. Someone says they don't believe yet. I don't believe either. Someone already told me this is going to explode, right? But this is kind of what I had in mind when I looked at this. So I was like, yeah, let's see if this works. Otherwise, we have to go back to the drawing board and start messing around with pointers, and that sounds like a lot of work.
Now, do we just read message text or whatever we did?
Can check message buff to see if the flag is there. Now, how do I want to look at that? We could print byte by byte. Can we do better? Oh, wait. Can we just cast the byte? Okay, we can just print F. How big did we make this thing? I want X hex 800 in theory. Okay, I like your, oh no. The tabs, man. The tabs. Okay. I like your simple approach here. We'll just %C with no new line, no anything. Message buff I.
G in there.
And that's just going to spew it out here. All
Do
right.
we want message buff I, or do we want, because message buff is our type and then it's the message.
Do I care?
Oh, I guess we could just print out the long time.
So think about what we're doing here again. Like, so the beginning of this is that message ID, right? That one that we sent. And then it's whatever happened to be in the message, right? Which will be, I don't know, maybe 0, maybe whatever random bytes. And then it will be maybe a flag, maybe not, maybe some random bytes. Then it'll be maybe a flag, maybe not, right? I'm literally just saying, give me every byte and make it look like a character, byte by byte. It is going to just, if we get to here, if it doesn't explode, it is just going to just output a large number of characters to the screen, and hopefully somewhere in there is, we can see a flag-like value, right? That is the degree of fanciness I am offering today. Okay. We wrote a lot of code. That's not bad. That's not bad. Message buff I doesn't like that, and that's because message buff, we made it a proper struct.
So yeah, we want message buff.
Ah, you want message buff buff? Okay, all right. That's not too bad for how much code we just fired out there, right? That is a...
Can you not do exit without doing standard lib?
It's a warning.
I guess if we're trying to call exit, we float up anyway. So
Right, like,
we might as well do more.
You know, if I made the warnings go away, it didn't seem to have a problem with it. Yeah, now it's just complaining about type stuff. Yeah, you know. But if you just do this, you feel so much better about your code. Okay? Everyone will tell you -W is far superior to wall. Okay? This makes me feel like a champion. All right. Now people are praying for my code. Yeah, I don't. I'm gonna restart the VM. It seems like a reasonable thing to do here. We're coming up on time, so if we run into this pointer thing that Twitch has promised me is happening, it's gonna be a sad day. It's gonna be just like the last one. I don't know, man. Figure it out.
Last time I think you just got us to well, okay, we still needed to fix some pointers, but like I feel like we got to a pretty good spot.
I feel like, you know, basically as long as this gets through the message stuff, I'm calling it a win. Yeah. Here we go. Bad stuff happened. Wah, wah, wah. But now we have some idea.
Yeah.
And interestingly, let's see, if we go over here and get our VM logs, we did make some bad stuff happen. What bad stuff happened?
Yeah, it's spraying flag everywhere.
That's a lot of, yeah, that is our spraying flags. This is our Kheap object. This is where bad stuff happens.
Why did the device get released?
Slab free. Did I not block?
That's possible. Yes. Like, I don't know why he released what you call. Do we need to block it again?
Okay. So that was educational. Let's restart our VM. Let's go take a look at our code. I did not block. I decided to remove the single most important line. Oh yeah, we don't. You know what? We don't want to see any of that. There we go. There's no hurt feelings here. The permission denied is coming from
Oh, I see.
P error. Should be man 3. Yeah. And so P error, which I'm also not including, produces a message to standard error describing the last error encountered as well as your happy message. So the last error encountered was permission denied. Okay. What was I doing? GCC-w do.c. Okay. Bad stuff happened. And logs, where's our bad stuff happening? How or where is that happening? Well, let's take a look here. It is after we open, we get device released. Let's go take a quick look here at Binja. We are calling free, right? But what the message that we're triggering is Kheap release, which should happen on close. Which I'm not closing anything. Okay, you know what? Let's not be fancy. Because you know what Pierre probably does?
Allocate something.
Well, you know what virtually everything does?
Do we want to put somewhere and be like we're trying to do?
All right, good old printf debugging.
Yeah.
I'm digging it. Where are we going?
Yeah.
Puts about to send, about to message send. Puts about to overwrite. Use after free. What else do we want? About to message get. About to free front FD. That's like where we saw it, right?
Yeah.
Okay. We are already there. About to message send, and then bad stuff happens in message send. Okay.
Is it still
It is still complaining about freeing the slab after message send. clearly the answer was to use 39.
Uh-huh.
Yeah, Twitch might have been onto something.
Interesting.
Maybe they weren't.
Let's see if this straw will help us.
Yeah. See if we get something different there. We did compile. We are good. We fire. Bad stuff still happened. VM logs. No, VM logs. VM logs. That looks the same. Damn. Okay. We are at slab tree plus hex 199. I'm not going to run late, so we will end up calling it here, which I like because that means I didn't solve it for you. But I'm curious about. I'm not in the right kernel version. 679. What could it be? Slam free. What's the actual error? Where are you seeing that? Oh, slub C444. Oh, that's is that's not where I am. slub.c. I thought I followed the call stack.
Yeah.
Slab free. Am I in slub.c? I am in slub.c. And it's saying 448. Or 48.
Oh, well, so somehow we're double free.
Naive detection of double free or corruption. So I know why we're getting the naive double free. I don't know why we aren't blocking to avoid it, though.
Right. Because, like, I think when you call Heap release, it calls free. We already freed that thing.
Right. When we close the kernel module, it tries to free.
Right.
And we've already freed it using our 5703. And we're only doing it once.
Because it doesn't even get to any of the other things. Oh, is the kernel tag unrelated? Because, like, if we p error out, we just exit, and then that, like, or if we error on message send, we just exit, and that will probably trigger the kernel tag. We're just hard exiting. Cool. So we're failing to message things.
We're failing to message things. Because we're failing to message things, and we wrote fancy code that actually checked our error state, we are exiting early, which is causing us problems.
Following good code practices.
Those dang coding practices. No, your clock and my clock are a little bit different. I'm not going to go over time. I'm just going to end the stream and say, good luck, guys. You got like 4 days. Man, it's not my problem. It's yours. So that means we probably want to take another look here at message send and figure out what we are doing incorrectly here. Like maybe we are creating just hypothetically, right? Maybe we're creating a queue we don't have access to. then we're trying to send on it, right? Maybe we need to create a private queue. Maybe our token is bad, right? We need to investigate what's going on there with the man pages to figure out why that behavior isn't working.
Cool.
I'm just curious because I do have, by my time, like 3 minutes. And for the record, I go an hour over time. Every office hour is by design. Like, this is a slotted hour, and I run through 2 just to try and like have some quality time here with you guys and hopefully be helpful. There was somebody on Twitch that said that they had this working and ran into some pointer issues. Does that person who claims to have made it past here have a suggestion or immediate answer that I will reiterate to the masses? Let's see. Yeah, give it like 20, 30 seconds for the Twitch delay. Oh, suddenly it wasn't weird pointer stuff. You got as far as I got. That's fair. That's fair. It looks like they realized after the fact that they were encountering a similar error, but they hadn't reasoned about what was going on. So once again, we went through kind of reasoning about the heap. But we ran into some specific detail here. I think this one really is somewhere in the man pages as far as why is message send failing. So if we can figure out what needs to be changed there, hopefully we can get past that and this approach makes sense. Now, if this approach doesn't make sense and for whatever reason we can't fix that, then we have to dig deeper into pointing the pointers to creating primitives. But hopefully it is as simple and straightforward as our monkey brain wants it to be. Any other questions from you guys? No? Okay. Somebody says they just rip my code and assume it works. Yeah, that's literally why I have a standing rule of like I try not to solve things or write code. I've learned better. This module is just not super conducive to that at the moment. With that, I will leave you all. If you do get stuck, please cry on the Discord, and hopefully y'all can help each other make your way through this. With that, I will see you on Tuesday. Next week is our last week of classes. Finals week comes after that, but there will likely be no class because final schedule is its own thing for Twitch people. So I'll see y'all on Tuesday. Goodbye and good luck.